Hi everyone, this is Dr. J. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology. So in this video, we are discussing the numerical methods and integral transform course. In that course, we are going to discuss inverse Laplace transform. In the previous videos, we have seen how to find out the Laplace transform for the function and how to transform the function from time domain to frequency domain. Now in this inverse Laplace transform, we are transforming function from frequency domain to function in time domain. So first we will take the definition of Laplace transform. So inverse Laplace transform is a mathematical tool which is used to convert from a function from frequency domain, so that is S domain, to time domain. So in the previous we have taken while we were discussing the Laplace transform, so we have taken t domain, and we by applying the Laplace transform for this function which is in t domain, so this is converted into a frequency domain. So in order to transform a function from time domain to frequency domain, then we can take the help of Laplace transform. Now reverse. Now the given function is in the frequency domain. Now we are converting that frequency function from frequency domain to function in t domain. Then we have to take the help of inverse Laplace transform. That inverse Laplace transform is denoted by L inverse. This is, we can call it as a inverse Laplace transform operator. So this is very important in order to solve the differential equations using the Laplace transform techniques. And similarly, we can use this inverse Laplace transform for analyzing the electrical circuits, in the study of heat transform, and in the modeling mechanical systems. So now we will go for the definition of this inverse Laplace transform. So that Laplace transform in the previous videos we have taken as Laplace transform of f of t is equal to f bar of s. So this f bar of s, we can call it as a Laplace transform of that function f of t. So f bar of s is the Laplace transform of a function f of t, that is L of f of t is equal to f bar of s. Then f of t is called, so now if you send this L to this side, it becomes L inverse of f bar of s is equal to f of t. So here this f of t, we can call it as a inverse Laplace transform of f bar of s. So that's here we have taken this one. F of t is called inverse Laplace transform of f bar of s, and this is written as f of t is equal to L inverse of f bar of s. So now from this video onwards, we are going to take the function from frequency domain, that is in terms of f bar of s. Now by applying that L inverse Laplace transform for f bar of s, we are going to convert that function in terms of f of t. So now let us take some important formulas in the inverse Laplace transform. So no need to worry about this inverse Laplace transform formulas. We can take the help of Laplace transforms, and by using that Laplace transform formulas, we can get the inverse Laplace transform formulas here. So first we will take one example. How can we derive inverse Laplace transform by using the Laplace transform? So suppose in the previous videos we have derived the Laplace transform of k is equal to, that is k by s. Suppose if you replace k with 1, so we will get Laplace transform. We know that Laplace transform of 1 is equal to 1 by s. Now you send this L to this side, so it becomes L inverse of 1 by s is equal to, so whenever we have L inverse of 1 by s, then we can take the inverse Laplace transform of 1 by s is equal to 1. And similarly, we have seen Laplace transform of e power at, Laplace transform of exponential function, we have that value is equal to 1 by s minus a. Suppose whenever we get inverse Laplace transform, you send this L to this side, So it becomes L inverse 1 by L inverse of 1 by S minus A. Whenever we are having a function f bar of S in this form 1 by S minus A, then we can take this value is equal to e power at. So from this it is very clear that once if you are perfect with this Laplace transform formulas, then by using that formulas we can get the inverse Laplace transform formulas. So this is the list of inverse Laplace transform. So now in the Laplace we are having a Laplace transform of e power at is equal to 1 by S plus A. Now you send this L to this side, it becomes L inverse of 1 by S plus A is equal to e power minus at. And we have proved this Laplace transform of t power n is equal to n factorial by S power n plus 1. Now send this L to this side, it becomes L inverse of, so L in n factorial is nothing but a constant, so we can take that constant outside and we can send that constant to this side, it becomes t power n by n factorial. So like this we can take the formulas in the inverse Laplace transform. And similarly Laplace transform of sin at, we have the standard formula, that is a by s square plus a square. Now you send this L to this side, it becomes L inverse of 1 by s square plus a square, or we can take L inverse of a by s square plus s square. This can be written as sin at. Suppose if we send this a is nothing but a constant, so we can take that constant outside that L inverse. So now send this a to this side, it becomes L inverse of, so L inverse of 1 by s square plus a square, we can take this value as 1 by a into sin at. And similarly we know that Laplace transform of cos at is equal to s by s square plus a square. So now send this L to this side, it becomes L inverse of s by s square plus a square equal to. So whenever we are having a function in this form, like suppose L inverse of s by s square plus 2 square. Suppose while you are finding the inverse Laplace transform for this type of functions, then we can use this standard formula L inverse of s by s square plus a square. So we have that formula L inverse of s by s square plus a square, we can take that value is equal to cos at. So here in place of a, so now you compare this and get the value of a. So here we are having 2, so this can be written as cos 2t. So this is the way how we can apply this inverse Laplace transform formulas. And similarly, so whatever the concepts we are learning in the Laplace transform, by using that concepts you are going to derive the formulas in the inverse Laplace transform. So these are the list of formulas we are having. So we have to, no need to remember this separately. So once if you are perfect with the Laplace transform of form standard functions, then by using that we are going to derive inverse Laplace transform formulas. So these are very important formulas we have to remember. Now by using these basic formulas, we will see how to find out the inverse Laplace transform for given functions f bar of s. Now this is the function he has given. Find the inverse Laplace transform of s square minus 3s plus 4 by s cube. This is the function he has given. For some time you consider this function as f bar of s. So for this f bar of s, we have to apply the L inverse, that is inverse Laplace transform. So once if we apply inverse Laplace transform for this function, what will be the function in terms of t? That is, we have to get the value of f of t. Now we will see how to apply this inverse Laplace transform in order to transfer the function from frequency domain to time domain. So now inverse Laplace transform, this is the function we are having. So once you concentrate on the function, so once if you observe this function, this is of the form a plus b plus c by d. So in the numerator we are having multiple terms, whereas in the denominator we are having a single term. So whenever we are having like this, then we can take this as a by d plus b by d plus c by d. So you divide that numerator with this denominator separately. So you will get L inverse of, so first term is s cube by denominator is s cube minus 3 is a constant, so we can take that 3 outside. So we can take that 3 outside. So next s by s cube plus 4 by s cube. So s cube gets cancelled, you will get L inverse of, so s cube you will get 1 minus 1 s gets cancelled, you will get 3 into 1 by s square plus 4 into 1 by s cube. So this is the way you will get this value by using this one. A plus b plus c by d can be written as a by d plus b by d plus c by d. And now we have the linearity property of inverse Laplace transform. Whatever the linearity property we have applied for the Laplace transform, you apply this linearity property for inverse Laplace transform also. That is L inverse of first term, L inverse of second term, L inverse of third term. Separately apply L inverse Laplace transform for each term. So that is given by L inverse of 1 by s, sorry here s square. So L inverse of 1 by s, L inverse of 1 by s square plus L inverse of 4 by s cube. So just now we have seen L inverse of 1 by s. We have the formula L inverse Laplace transform of 1 is equal to 1 by s. You send this L to this side, it becomes L inverse of 1 by s is equal to 1. So in this we can take this value is equal to 1. And here we have the Laplace transform of t is equal to, so 1 by s square. Now send L to this side, you will get L inverse of 1 by s square is equal to t. And similarly we have the formula Laplace transform of t power n. Use this formula. So this can be written as n factorial by s power n plus 1. Now here we are having, we send this L to this side, 1 by s power n plus 1 is equal to t power n by n factorial. Now you take this one, 4 is a constant, so we can take that 4 outside. So that is L inverse of 1 by s cube. So you convert this s cube in the form of s plus n plus 1. So you will get this value is equal to L inverse of 1 by s power 2 plus 1. So this can be written as t square by 2 factorial. So like this, once if you remember these basic formulas, we can find out this L inverse here. So if you simplify this, finally you will get that value is equal to 1 minus 3t plus 2t square. So this is the way how we can apply these basic formulas to find out the inverse Laplace transform for the given function. Let us take one more example here. So this is important. So L inverse of 2s plus 1 by s of s plus 1. Now this is our f bar of s. Now for this f bar of s, if you apply inverse Laplace transform, then you will get a function in terms of t. That f of t we have to find out this. Now let us see how to apply this inverse Laplace transform. So our task is, whatever the given function he has given for f bar of s, we have to convert that given function in terms of our standard formulas. That is the important thing we have to remember here. So after converting the given function into our standard formulas, then apply that inverse Laplace transform formulas, and then you will get our required function f of t. Now let us see how to use this. So this is f bar of s, 2s plus 1 by s into s plus 1. Okay, now we will see. You think of it how to reduce this function in terms of our standard formulas. Suppose If you apply the same one, a plus b by c, you will get 2s by s of s plus 1 plus 1 by s of s plus 1. So s gets cancelled, you will get 2 by s plus 1 plus 1 by, if you remove the brackets here, you will get s square plus s. Now for the first term we don't have any problem, because if you apply L inverse you will get 1 by s plus 1. So this is of the form L inverse of 1 by s plus a. We have the formula. We don't have any problem with the first term. Now take the second term, L inverse of 1 by s square plus s. So can you find any standard formula of this type, 1 by s square plus s? We don't have this. Suppose we have the formula in the form of L inverse of 1 by s square plus a square. Some constant term will be added to this s square term. But here we don't have the constant term. This is s. So when we apply this procedure, then for the second term, we don't have the standard formula to find out the L inverse. Now, how can you split this function in terms of our standard formulas? This procedure for the second term, it is not applicable here. Then how can you overcome this difficulty? So for this purpose, what I am doing is, I want to go for the another option. That option is, so this is the function he has given. Now in here, in the numerator we are having 2s. So I want to convert the 2s as s plus s. This is another option I am having. Suppose if we take 2s plus 1 by s of s plus 1. Now let us take 2s. We said that 2s, I want to take the 2s as s plus s and write this plus 1 as it is, s of s plus 1. Now by using this technique, we will see how you will see is it reducible to our standard formulas. Let us take. So now you consider the second and third term as a single term. So that is s plus of s plus 1. So now this is of the form a plus b by c. So this can be written as s by s of s plus 1 plus s plus 1 by s of s plus 1. Now this s gets cancelled, s plus 1 gets cancelled. Finally we will get 1 by s plus 1 plus 1 by s. Now on both sides if we apply L inverse, so you will get L inverse of this one, L inverse of this one. So we have the formula L inverse of, this is of the form 1 by s plus a. We have the formula, and this is in the standard formula L inverse of 1 by s. Now for the both terms we can apply our standard formulas. If you convert this function numerator 2s plus 1 as s plus 1, then we can reduce that into a sum of two terms, and for that two terms if we apply the inverse Laplace transform, then we have the standard formulas to find out that inverse Laplace transform. So like this we have to analyze the given function, and finally we have to convert that function into our standard formulas. By using that standard formulas, then only it is possible to get our required L inverse Laplace transform. Okay, now let us see. So as usual, 2s can be written as s plus 1 by this. So now similarly this is a plus, you consider this term as b by entire this term as c. So a by c, s gets cancelled, so this is our remaining, and b by c, this s plus 1 get cancelled, you will get 1 by s. Finally this is the procedure we followed here. And now apply the linearity property, L inverse of first term plus L inverse of second term. Now we have the formula L inverse of 1 by s plus a. So what is our formula for L inverse Laplace transform of 1 by s plus a? This can be written as e power minus at. So now take this one, 1 by s plus 1. In our problem we are having s plus 1. So now compare this and get the value of a. So by comparing in place of a, here we are having 1, so we can take a is equal to 1. Now you substitute that a value in the standard formula. That is, you will get e power minus 1 into t. That is e power minus t. So L inverse of 1 by s plus 1, we can take this value is equal to e power minus t. So that is e power minus t, and this is our standard formula. So we have the formula L inverse of 1 is Laplace transform of 1 is equal to 1 by s. So send this L to this side, it becomes L inverse of 1 by s is equal to 1. So this is our 1. So like this we can find out the inverse Laplace transform for the given function. Okay. Now we'll take another example here. So this is our next problem. So this is our function. He has given f bar of s is equal to 3s by 4s square plus 25. So first what we have to do is, whenever we want to find out the inverse Laplace transform for the given function, first in that procedure, first you concentrate on the denominator. You concentrate on the denominator here. So once if you observe all the formulas of in the inverse Laplace transform, our formulas are in the denominator having s square plus a square. This is one denominator, and s square minus a square, and we are having the denominator s square plus a square whole square. So like this we are having the formulas. So once if you observe our standard formulas here, once if you go for the first slide, so here we have the formulas. So see, inverse Laplace transform L inverse of s square plus a square is equal to this L inverse of s by s square plus a square. So s square minus a square, s square minus a square. So all these four formulas, the coefficient of s square is equal to 1. So whenever in the given function, suppose if you are having any coefficient for s square except 1, then first we have to take that coefficient of s square common from that denominator. So because in our standard formula the coefficient of s square is 1, that is we want only s square. We don't want any coefficient for s square in the problems in order to apply the standard formulas. So now when you come to our problem here, the coefficient of s square, here we are having 4. We don't want this 4 here, because in our standard formulas we don't have the coefficient of s square as 4, 5, some constant. So just we are having only s square here. So now what we have to do is, we have to take that 4 common from the denominator. Then only that denominator is converted into our standard formulas. Okay. So here you consider this one as A, and this one as B, and this one as C. Separately you take this. So L inverse of A by C, that is 3s by denominator, minus 8 is a constant, so we can take that 8 outside this L inverse. And if you take 8 outside inside this, we are having 1 in the numerator, and the denominator is 4s square by 25. So as we discussed now, so I want to take 4 common from the denominator. So already in the numerator we are having 3, which is a constant, so take that 3 outside. So this is L inverse of 3s by 4s square plus 25. This is our function. So 3 is constant. You take that 3 outside from the inverse. And now we have to convert 4s square in the form of only s square. Now for this purpose, I want to take that coefficient of s square 4 outside. That is, it becomes in the denominator as 4. The remaining one is s by s square plus, we don't have 4 here in the second term, so we can divide that 25 and multiply with 4. So 4 by 4 you will get 25 by 4. So this can be written as 3 by 4 L inverse of S sub by S square plus 25 by 4 can be written as pi by 2 whole square, because here we are having the formula L inverse of S sub by S square plus A square. So we have to convert that constant term in the power of 2, that is 25 can be written as 5 square, 4 can be written as 2 square. For both numerator and denominator we are having a common power, so that can be written as S by 2 whole square. So this is the way how we can take this one, and follow the same procedure for the second term also. You will get this. Now simplify this. So what is the formula for this one? L inverse of S sub by S square plus A square. We have this value is equal to cos AT. What is the value of A here? You compare this with this. So in place of A here we are having 5 by 2. So replace that, you will get cos 5 by 2 into t. And here now we don't have the s in the numerator for the second term. So now we have to apply another formula, L inverse of 1 by S square plus A square. So this can be written as 1 by A into sin AT. 1 by A into sin AT. Now use this formula here. So if you use this formula, L inverse of 1 by S square plus A square, this is equal to 1 by A into sin AT. So here A is equal to 5 by 2. So you will get 1 by 5 by 2. This can be written as 5 by 2 by 5 into sin of 5 by 2 into t. Now cancel this, 2 ones, 2 2's. So you will get 3 by 4 cos 5 by 2 into t. And here, so here 2 ones, 2 4's. So 4 by 5 sin 5 by 2 into t. This is our procedure to find out this type of. We are not using more complicated formulas, just we are using the basic formulas in the inverse Laplace transform. So in this video we have seen what is inverse Laplace transform, where we can use this inverse Laplace transform, how to derive the formulas of inverse Laplace transform, and by using that basic formulas we have seen how to find out the inverse Laplace transform of f bar of s. So in the next video we will go for the inverse, we will see how to find out the inverse Laplace transform using another technique, that is partial fractions. How to apply the partial fractions to find out the inverse Laplace transform for the given function. So this video explains how to find out the inverse Laplace transform for the simple functions which are easy to convert into a standard formulas. And now if you take some more complicated functions or some big functions, then we have to take the help of partial fractions to find out the inverse Laplace transform for such type of functions. The next video we will see this inverse Laplace transform using partial fractions. Thank you.